The hidden truth behind the 3-eye Atlas flyby. October 7, 2025 marked a moment that sent ripples across the world when the European Space Agency unveiled the first official photos of 3-eye Atlas, the interstellar comet sweeping past Mars. Everyone expected a breathtaking revelation, but instead the reaction was disbelief and frustration. A faint, indistinct speck appeared where clarity was promised. Silence followed from NASA, China, and the UAE, and no trace of the sharp imagery people had awaited. Why did the most anticipated Martian flyby in years stir only confusion and secrecy? And what are the agencies concealing behind layers of technical explanations when amateur astronomers began releasing clearer pictures than billion-dollar missions, and whispers of impossible chemistry emerged? It became clear that the real story was just beginning at 9:22 UTC on October 7. ESA published the first 3-eye Atlas visuals across its channels, and within minutes, every major science page and meme account shared the same disappointing frame. A dim pixel lost in background static by noon. The term ESA Cassis trended in multiple languages, and hashtags like fuzzy dot and where are the pics surged across social media, dissecting every pixel. Frustration deepened as users posted side-by-side comparisons showing backyard telescope captures that appeared sharper than the billion-euro Mars orbiter. People accused ESA of withholding information, pointing to the eerie silence from NASA, China, and the UAE. With every unanswered question, public suspicion grew stronger. The Cassis camera aboard the ExoMars Trace Gas Orbiter was designed to image the Martian terrain, not interstellar objects 30 million kilometers away. Its limitations became obvious. Each pixel covered about 340 kilometers, easily enough to engulf volcanoes, and far too coarse to capture a nucleus only a few dozen kilometers wide. Its resolution of 11.36 microradians per pixel created an unbreakable limit. No matter how perfect the focus or exposure, the comet would remain a blur light scattered across the detector. Nick Thomas, principal investigator, admitted it was a challenge even to detect the faint object thousands of times dimmer than the Martian surface. After stacking exposures and enhancing signals, the team produced the best image possible, a hazy dot, the result of physics, not conspiracy. The vast coma blended into space, the core lost completely. The camera could prove presence, but not detail. What the world wanted was a portrait. What science could offer was a fingerprint. Real answers would require different instruments or orbits entirely. NASA high-rise camera aboard the Mars Reconnaissance Orbiter was expected to deliver that breakthrough, capable of mapping rover tracks from orbit. It should have captured at least a few pixels of 3-eye Atlas, but just as the encounter began, the U.S. government shutdown halted everything. Command uplinks, data logs, and public releases froze. Even planning files vanished from the usual archives. Amateur and professional astronomers refreshed in vain, waiting for new imagery, while NASA remained silent. Speculation turned toward China. Tianwen-1 and the UAE Hope both had tracked the comet, yet neither released statements or pictures. Some pointed to the shutdown as the reason, others asked why 3 agencies across continents were all quiet at once. The longer the silence, the louder the rumors became. Every missing image fueled a sense that the world's most advanced cameras were being silenced. High-rise absences became the focus of conspiracy. The missing crown jewel left a vacuum quickly filled by speculation and skepticism. Soon after ESA blurry release, the image wars erupted. Amateurs across the world posted their own versions. Some stacked dozens of frames while others applied AI filters claiming to reveal hidden structures. By October 9, the internet had divided into believers and doubters. One side saw a defined nucleus, maybe even a tail, suggesting amateurs had outperformed official missions. The other warned of illusions and overprocessing. Melbourne comet hunter Maya Trin became the face of the believers. Her enhanced sequences, annotated with streaks and shapes, went viral, gathering thousands of shares. Critics responded with side-by-side tests, showing how stacking could amplify noise, and how AI sharpening only emphasized artifacts, not truth. The debate turned deeply technical, as users discussed sigma clipping, deconvolution, and pareidolia, trying to reverse-engineer truth from numbers. Experts reminded everyone that even the best stacking could not overcome Cassie's massive pixel scale. Each aggressive enhancement created more illusion than clarity. The online hunger for answers grew faster than real data could satisfy, and the call for genuine, transparent analysis intensified. While rumors circulated anonymously, attention shifted toward measurable evidence, numbers that could be tested, trajectory paths, and radio readings. Until such data appeared, speculation ruled on the surface of Mars. Mallory Lefferland, shift lead for the Perseverance rover, initiated an unscheduled experiment, though the rover navigation camera was never intended for comet tracking. She ordered a 10-minute continuous exposure session aimed at the sky. On October 7th, the images revealed a faint streak, 1 pixel wide, stretching diagonally across the frame. At first, it looked like a glitch, but timing matched 3I Atlas predicted pass precisely at 90 km per second. The comet would have covered roughly 54,000 kilometers during that exposure, fitting the length of the streak if it lasted the full sequence. The blur represented motion across distance, a faint, fast-moving object, too dim to isolate frame by frame. Yet, if exposure time had been shorter, the same streak could only mean a much nearer source, possibly in Martian orbit, without access to the original data headers. This crucial variable stayed hidden, making every calculation uncertain, whether the trace came from the comet or something closer. Lieferland's decision, however, transformed rumor into testable evidence. The streak became the first solid metric amid chaos, a 54,000-kilometer question challenging all assumptions. A line drawn from Jezero crater on that same night aligned almost perfectly with the region of the sky linked to the famous WOW signal recorded in 1977 by Ohio State Radio Telescope. A 72-second burst at 1420 MHz never explained. Atlas was passing only degrees away. The coincidence revived old debates. Quick calculations flooded forums estimating that to match the WOW signal strength from a source 600 astronomical units distant would require over half a gigawatt of directed power. Yet despite the alignment, no observatory released hydrogen line data, no listening campaign, no raw spectra, not even confirmation of silence. The absence of radio results deepened the mystery. The question grew, why was no one performing the simplest test? On October 29th, 3I Atlas slipped behind the sun, disappearing into solar glare so intense that even top telescopes lost sight for nearly 40 hours. Its elongation dropped below safe observing limits, and with it the world entered a blackout. Theories multiplied. Some predicted a natural outburst or disintegration common for comets near perihelion. Others speculated about deliberate maneuvers hidden from view. The Galileo project, dedicated to searching for non-natural technology, initiated continuous monitoring across all possible channels. But with the comet invisible-only models and speculation remained, everyone waited for its re-emergence, expecting new clues about brightness trajectory or fragments that could redefine its story. By early November, astronomers began their diagnostic checklist, measuring brightness curves for signs of fragmentation, and running orbital simulations to detect even the smallest deviations. Each test a potential revelation. Did the comet fade normally or split apart? Did its path shift under jets or unknown forces? The JUICE spacecraft prepared for its turn, though its observation data would not reach Earth until well into 2026. Every new change in light or motion became a hint, and every data delay stretched global anticipation. October sky, however, held more than 3I Atlas, a near-Earth object labeled 2025 TF, had just skimmed past Earth unnoticed until the last moment, passing inside GPS orbit range, proving that even now the sky holds surprises beyond constant watch. Meanwhile, two other comets, C2025A6 Lemon and C2025R2SW, displayed erratic brightening and close passes, reinforcing that the cosmos remains unpredictable and full of close calls. On October 7th and 8th, 2025 ESA official images of 3I Atlas, a single blurred pixel, ignited debate across the planet. The lack of detail stemmed from hardware limits not to see yet. The synchronized silence from NASA, China, and the UAE kept doubts alive despite viral amateur efforts. No confirmed evidence has surfaced of unusual emissions or intelligent control. The Perseverance navcam streak fits motion blur from an object moving at 90 km per second. Though alternative explanations cannot be excluded, as 3I Atlas vanished behind the sun and reappeared weeks later. Scientists awaited new data to judge whether it survived or fragmented. The delayed readings from JUICE and the unnoticed flyby of 2025 TF underline a sobering truth: humanity's vision of space, though powerful, still sees only fragments, and the real identity and purpose of 3I Atlas remain an unsolved testament to how much we still do not know.